Hello everyone, welcome to the video lecture of the subject Digital Electronics, and this course is dedicated to almost all the branches. All the branches are going to study this course, and the topic which we are going to study is the design of combinational circuits with the help of ROM. Right? We have already covered the combinational circuits. We can design any combinational circuit with the help of multiplexer or decoder or any other circuits, right? So we all have covered the combinational circuits and sequential circuits. Now these circuits can also be designed with the help of memories also, right? So what basically is ROM is? Your ROM ROM is defined as a read-only memory. It is a large-scale integration combinational circuit. Large-scale integration means it has millions and billions of MOSFETs inside that IC, right? So ROM circuits can store binary words of a fixed length in each cell, right? Each cell will be of fixed length, and we can store n number of bits in that. Each cell has associated with the binary numbers usually referred to at address. So now because we have this memory and it has n number of locations in that, right? So we have to read or write data to one particular location. So to go to that location, we use these address signals. So the number of cells is determined by the address lines of the bits. So while designing any memory, we always use the address lines. Okay. So we are going to use the address lines. So in case of ROM, the storage is non-volatile. Non-volatile means whenever when the data remains in the circuit, even when the power is removed. In contrast to that, volatile storage such as random access memories, RAM circuits, they cannot attain the stored binary information when the circuit is disconnected. So in any memory circuit, if you have k address lines, and the number of bits and n number of bits are there in each cell, so the output bits are n, and the ROM size can be defined as this 2 raised to the power k into n. So in fact, the ROM circuits can be seen as the combinational circuit capable of storing the large truth tables whose outputs are corresponding to the address, whose inputs are corresponding to the address signals. So the first ROM circuit produced has the data stored at the moment of the fabrication, and it was not possible to modify the content after that. So once the circuit is fabricated, it is programmed. You cannot change its programming. This was the previous ROM structure. That is the main reason why they are known as read-only memory. We can only read the data from the ROM ICs. We cannot program them initially. That is the case decades before. But the process of storing data into ROM chips is usually referred to as programming, right? So this programming is done only during the time of fabrication. Your circuits are finalized, and then they are programmed in. Then they are fabricated into the IC. But the technological advancement allow the creation of the ROM circuits which could be rewritten after fabrication with or without external interference. Usually this ROM circuits can be classified based on their reprogramming technologies. So the first one is the mask ROM, mask read-only memory. This type of circuit is programmed at the manufacturing time, and it cannot be reprogrammed after that. This process is usually the cheapest when the manufacturing is done for the large quantities of identical ROM circuits. Next we have the PROM. PROM stands for the programmable read-only memory. The data can be stored after the manufacturing process or in the field, and the method of programming as well as the number of times it can be programmed gives away to number of subtypes. So we have these subtypes. First one is your one-time programmable memory, one-time programmable ROM. It can be programmed only once by the user. Next we have EPROM. EPROM stands for erasable programmable read-only memory. In case of erasable programmable read-only memory, the data which is already written in the ROM IC, it can be erased with the help of some light, and generally we are going to use the UV light for this purpose. We are going to use the UV light for this purpose. We are going to flash, there is some small window over the ROM ICs, and over that window we are going to pass the UV light. With the help of that UV light, your data can be erased and we can reprogram that IC. So this type of ICs has the limited number of erasing time, that how many times you can erase the data. This is limited. Next we have the double EPROM. Double EPROM stands for electrically erasable programmable read-only memory. In case of electrically programmable read-only memory, it can be erased electrically instead of using the UV light. Lastly, we have the flash memory. In case of flash memory, this is the more modern version of the electrical erasable programmable read-only memory. The erasing and rewriting phase are faster as compared to your another memory ICs. So this is some basic classification of your read-only memory. This is the read-only memory. We cannot write in those ICs, but we can program that. So this is the basic structure of your ROM, where your K is the address lines. We have K address lines and n number of outputs will be there. Okay, so it consists of some decoder circuit. For example, we have this 5 into 32 decoder, 5:32 decoder. So it is 2 decoder. We know that whatever the address lines, 2 raised to the power 5, that is your 32 output lines will be there, right? So 8, we have these, we have n number of output lines, that is the dependent on memory size, that how many outputs we need, right? So in this way we can it has 8 output lines and 5 address lines. So this is the programmable read-only memory. Here we have the fuses. All connections are connected to this, and we have the fuse over there. Whatever link we want to make, that fuse will be closed and it will be connected, and rest of the fuse will be in open condition. So now we can realize any circuit with the help of ROM ICs. For example, we have to analyze this function with the help of ROM structure. So we can see here that we have to analyze these 4 functions: F1, F0, F1, F2 and F3. So 4 outputs will be there. Okay. Four outputs will be there. Okay, and here we have the maximum number 7. Okay, so maximum 7 outputs, 7 outputs we need to have, and to represent this 7, that is 1 1 1, we need minimum 3 signals. So 3:8 decoder I am going to use. I'm going to use this 3:8 decoder. Okay, so 3:8 decoder. So 3 input lines and 8 output lines are there. Here we have the 8 output lines. In the memory structure, these are connected to the address lines. These will be connected to the output lines, and here we have the outputs. Okay, so these are my programmable, these are my, sorry, these are my programmable links. Okay, so F0, from this equation F0, here we have the connections on 1, 2, 3, 5 and 7. So here we can see that I have marked these X over 1, 2, 3, 5 and 7. So these links are connected, rest all the links are open. Okay, so whenever your appropriate address lines are there, this on these lines we are going to have some output. Similarly, F1 0, 2, 5, 7, F1, so we have 0, 2, 5 and 7. These links are programmed, and where you need the connection we mark X, in rest all the connection will be treated as no connection. Then 2, 0, 2, 4, 6, 7, 0, 2, 4, 6 and 7 are connected to have the output F2. Next we have F3 0, 2, 4, 7, 0, 2, 4 and 7. So the output of each is passed to the OR gate, and at the output of OR gate we are going to have the respective function. So this way we can realize any combinational circuit with the help of ROM, or any decoder. So let us analyze the full adder with the help of ROM. So first we are going to write the truth table. Write the truth table of full adder. In case of full adder, we know that we have three inputs A, B and C in, and the outputs are sum and carry out. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, anything left? 0, 1, 2, 3, 4, 5, 6, 7. Okay. So 0 plus 0 plus 0, 0 and 0. Sum 1 carries 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1 and 1, 1, right? So the sum, we have 1, 2, 4 and 7. 7 please. Carry out, we have 0, 1, 2, 3, 5, 6 and 7, right? So 3:8 decoder, again I am going to use 3 input lines which will be connected to the address lines of the room. So we have A, B and C in, and eight output lines. So another representation, in another representation, all the lines are all the lines are connected to OR gate, and here we have the fuse. Here I'm going to have the fuse, whatever some fuse links will be there. So these are marked as I have less space, so these fuse are marked in this way. So this way also we can also make the connections. All lines are connected to OR gate, and wherever you have the connection, fuse will be connected, and rest all the fuse will be open. Okay. So we have 0, 1, 2, 3, 4, 5, 6, and 7. So on the sum side, I'm going to have this 1, 2, 4, and 7. And on the carry, this is the sum, and carry 3, 5, 6, and 7. We have the carry out circuit, right? So this way we can design any decoder, any circuit with the help of ROM. This will be connected to the address lines, and these are your final circuit outputs. So next is the implementation of ROM, which I was telling you that we have this kind of connections also. For example, we have two inputs. A1 and A2, and we have outputs F1 and F2, right? So two inputs we are connected to the decoder inputs, and from there we are going to generate the 4 outputs, and these are the opening the links is referred to as programming the ROM. So this way we can in case of F1, we can see that D1, D2, and D3 are these 3 lines are connected, right? 3 lines are connected, and so 3 lines are connected, and this is the open, right? And similarly for the F2, 1 and 3rd line are connected, rest 2 lines are open. So these fuse are open. Okay. So this way we can also make the representation and analyze any function. So let us check one more example. Design a combinational circuit using a ROM, and the circuit accept 3-bit number and generate an output binary number that is equal to the square of the input numbers. So the first step is to drive the truth table for the given statement. So in case of the given statement, if your number is 0, its square will be 0. If it is 1, its square will be 1. If it is 2, its answer will be 4, 3, right? So this way we are going to proceed further. 9, right? So the first step is to drive the truth table for the combinational circuit of the given statement, understand the given statement, and find out what we need to plot, right? Then 3 inputs are given and 6 outputs are needed. How 6 outputs are needed, that we are going to see. So with the help of 3 inputs, we are going to have 7 for 8 possible combinations. So 0, its square is 0, 1, 1. For 2, square is 4, then 3. Here we have 0, 1, 2, 3, 4, 5, 6, and 7, right? So we have 16, 25, 36, and 49 for 7, right? Now to represent this 49, I need this 6 output lines, right? 6 output lines are needed so that we can correctly represent this number 49 in binary, right? So next we can see that your B1 input is always 0. This B1 input is always 0 and your B0 and A0 are identical, right? So these two signals we are not going to connect. This will be B0 will be directly connected to A0 and B1 will be directly connected to 0. So the reduced table will be, we are going to have this much stored information. This much stored information will be there, right? So the minimum size ROM needed, it must have 3 inputs and 4 output lines. So 3 inputs are there and 4 output lines are there. Minimum 4 output lines we need. Okay, so 8 cross 4 ROM structure we are going to use, that is your 2 raised to the power 3, 2 raised to the power address line into output line. 2 raised to the power 3 into 4, 2 raised to the power address lines into, excuse me, into output line, right? So B0, we can see that it is connected to A0 because your B0 and A0 are identical. Then B1 is connected to logic 0 and here we have the 4 output lines B2, B3, B4 and B5, which will generate the square of the given number. So this way we can analyze any combination circuit with the help of ROM structures. So thank you so much for today's lecture. A few advantages and disadvantages of this ROM structure, that in case of ROM, the information stored in ROM is permanent in nature. We cannot, we can only read, we cannot write some, there are facilities with the help of which we can program the memories. The advantages are this, it has low cost, high speed and non-volatile memory. So thank you so much for today's lecture.